Hello and welcome everybody to today's presentation named Low Maintenance Multi-Cell Buried Structures Designed for Life. My name is Jan Leiko and I'm giving the presentation on behalf of the authors. Today's presentation will cover A465 scheme introduction, related geological and environmental constraints, selected option for the structure, and early thermal cracking design in comparison to the heat of hydration analysis carried out in finite element environment. And then we will summarize everything in conclusions. The structure is located on the A465 Heads of the Valleys in the heart of Wales, United Kingdom. The A465 forms one of the main east-west highway routes in South Wales. The highway also forms a part of Trans-European road network. The existing A465 was built in 1964 as a single three-lane carriageway. The existing single carriageway road is being widened through the Clydach Gorge, part of the Brecon Beacons National Park. Due to the local topographical constraints, the road had to be widened over the Carboniferous limestone caves Ogokelinen and Ogokeppel. The topography of the ground has created a steeply sloping embayment feature known as the divot at the cave entrance. Therefore, we call the structure the divot. An extensive cave system is close to the road surface. The caves accommodate natural bed habitat that must be protected and not disturbed. The discussed A465 section is being referred as Section 2, and as mentioned is a widening scheme where a single three-lane carriageway is being widened to dual carriageway. Costain was awarded the Section 2 contract by the Welsh Government in 2011, supported by a design joint venture formed by Atkins and CH2M Hill, which was in the meantime acquired by Jacobs. Construction of Section 2 commenced in 2014 and is due to be completed in 2020. The overall project cost of the contract is estimated to be £336 million. The chosen procurement route was early contractor involvement with the design and build phase carried out under the NEC3 Engineering Construction Contract Option C. Here on the slide you can see several photos from construction. Now let's talk about environmental constraints of the scheme. Section 2 is one of the most environmentally challenging schemes in Wales. The section includes a total of 40 statutory designated sites within 10 km of the route corridor, 23 sites of special scientific interest, 3 national nature reserves, 9 local nature reserves, and 5 are the European designated Ask Bed Site Special Conservation Area. The identified key issues along the route corridor were the effects on the lesser horseshoe bed population and the habitat known as Tilio-Assyrian woodland. On the left side of the slide you can see a plan view on the existing A465 shown by the gray lines representing carriageway boundaries as it crosses the cave system underneath. And on the right side of your screen you can see a few photos taken from the caves and one of the hibernating beds. It's not just the environmental constraints which are making this scheme difficult, it's also its geomorphology. The project has been assessed as geotechnical category 3 as it involves very large, unusual and complex geotechnical activities, earthworks and structures, and those involving abnormal geotechnical risks together with unusual and exceptionally difficult ground conditions. The historical and geological maps show that the area of the Clydach Gorge are underlain by strata of the Carboniferous limestone supergroup, which have been extensively quarried for limestone. Ogofgelinen at this location is formed in consolidated stone and clay. There may be no competent rock between the roof and the surface. Vertical fractures in the roof of the caves likely extending to the surface, with traffic here in the caves and water ingress obvious during wet periods. The current alignment of the A465 at this location is underlain by engineered fill comprising glacial till derived material which overlies limestones of the Clydach Valley group. On the right side of the slide you can see geological profile with respect to existing A465 alignment and caves elevation shown by blue color. Geological material properties are summarized in the table under the text. As said before, the divot refers to a steep geological embayment located at the westbound carriageway. At this location, the terrain is not wide enough to accommodate widened A465 carriageway. To accommodate verge of the westbound carriageway, a structure has to be built. Several options were considered. First option assumed building of a retaining wall on the geological feature, backfill the wall, and build remaining part of the carriageway on the top of it. However, this solution would introduce additional pressure on the cave roofs due to increased depth and traffic loads. Other option considered to span the divot with a bridge. This solution would require piles boring to the rock and large maintenance costs. Third option considered to build a multi-cellar concrete structure which is light and requires low maintenance. Cantilever attached to the side of the structure is wide enough to accommodate the new alignment. This solution does not impart any additional dead load about the caves, as it is lighter than excavated material, and along with additional live loads over the new carriageway width, the load is not greater than that on the existing carriageway. The light and low maintenance structure was proposed as a voided slab of a rectangular footprint with 3 chambers and cantilever edge to accommodate the widened carriageway. The overall length of the structure is 24 meters to bridge the cave system and allow ground bearing at a safe distance beyond the caves. The structure is in longitudinal elevation 5%. The overall width of the structure is 11.3 meters. It carries the westbound carriageway, including a part of central reserve. At the edge of the cantilever, it is proposed to have a concrete steel precast parapet. The voids are 2.6 meters wide and divided by concrete walls of 250 mm thick. The top and bottom slabs are both 250 mm thick as well. The voids were proposed to be filled with extruded polystyrene, which provides lost formwork for the top slab concrete. As this is a buried structure, majority of the concrete surfaces are in permanent contact with the surrounding soil and ground moisture. The structure was therefore designed to prevent concrete cracking due to early thermal actions related to cement hydration as a measure of controlling water ingress and improved durability. The reinforcement spacing was designed with respect to the concrete early age thermal cracking. To refine the early thermal strains calculation, a 3D FE model was developed for heat of hydration distribution analysis. The analysis considered the assumptions related to specified casting and curing requirements. Specific concrete mix design and 3 construction stages, each lasting for 5 days, were considered. Based on these assumptions, it was possible to analyze heat of hydration distribution across the structure after pouring and during concrete hardening up to the time when the temperature were uniform in the whole structure. Ambient ground and air temperature was assumed to be 21 degrees Celsius. Material properties such as convection heat transfer coefficient, radiation heat transfer coefficient, thermal conductivity, and volumetric heat capacity were set to default values for concrete. Exothermic behavior properties, weight of cement per unit volume, water to cement ratio, and cure temperature were set in accordance with Parallel Syria 660 calculation. In the figure is shown volume FE model developed for heat of hydration analysis. Each concrete member was modeled as a 3D volume and meshed with tetrahedral elements. This slide presents results obtained from the HOH analysis. The contour maps present temperature developing in each member in time, corresponding stresses and strains. First construction stage considered from bottom slab pouring and hardening and lasted for 5 days. The results demonstrate heat propagation at the center of the slab. Maximum temperature was achieved after 12 hours. After 5 days, the slab achieved the temperature corresponding to its surrounding. In second stage, the walls were poured. The temperature achieved its maximum after the same time as the bottom slab in the previous stage. The contours show how was the heat transferred from the walls to the bottom slab. After 5 days, where the walls naturally cooled down to the ambient temperature level. The last stage represents top slab pouring. The time scale for achieving maximum temperature and consequent cooling was corresponding to the previous stages. Remarkably, the contours show maximum temperature developed in the cantilever, from which was the heat transferred down to the supporting members. This table summarizes maximum temperatures, compressive and tensile stresses, and strains in each construction stage. The table can be found in the published paper. The results will be discussed in the following slide. The HOH analysis showed that the maximum temperature achieved in the bottom slab is 45.6 degrees Celsius. This is probably due to different boundary conditions at the top and bottom face of the base slab, while the bottom face is in permanent contact with soil with different thermal conductive properties. The top face is exposed to air. The maximum temperature achieved in all other members varies between 32 to 35 degrees. The other members are exposed either to air at both dominant faces or to air at one face and to polystyrene at the other. The temperature difference delta T is equal to 24.6 degrees Celsius and 11 to 14 degrees respectively. The maximum tensile stress achieved in concrete was up to 1 megapascal located in the top slab. The stress level below concrete tensile strength suggests that the crack will not be developed due to heat of cement hydration. Following the design principles according to Syria with the same concrete properties and boundary conditions, the differential temperature delta T used for calculation was 30 degrees Celsius. The results obtained from the calculations suggest cracking of the top slab with minimum 530 mm² required reinforcement area per face. Substituting temperature differential delta T with computed value by FEHOH analysis, the calculation results suggest that thermal cracking will not occur. Adopting the conservative design approach, it was found that the maximum calculated crack width is less than 0.1 mm. According to Eurocode 2 Part 3, the structure was classified as Class 1, where the water ingress to the structure should be limited by the crack width WK1. The limiting crack width value WK1 for this structure is 0.2 mm. Satisfying this criterion should result in effective self-sealing of a crack in relatively short time. The summary of remarks will be presented. The HOH analysis has shown that the maximum differential temperature achieved is less than the value obtained according to Syria C660. This suggests the early thermal crack calculation is more conservative than the FEHOH analysis. Consequently, the crack width and spacing according to Syria C660 is greater, since the HOH analysis had shown the stress lower than concrete tensile strength. The maximum hydration heat was achieved circa 12 hours after pouring. After 5 days, the concrete temperature was corresponding to external temperature. Syria C660 does not provide temperature difference for polystyrene formwork, however provides value of thermal conductance for polystyrene formwork, which can be set in FEHOH analysis. Even though the Divot structure may appear as a simple construction, Its design is a careful balance between significant environmental and geological constraints and minimizing construction costs and risks. The structure was designed to protect the natural bed habitat from collapse due to the potential increased traffic surcharge about the caves. The design of the structure was also carried out with respect to minimizing maintenance requirements. Close attention to the detail and producing a simple reinforcement arrangement will prevent excessive cracking and enhance durability of the structure for its design lifetime of 120 years. It should be said the Syria C660 was in the meantime superseded by Syria C766 and the calculated results need to be verified against the latest calculation approach. However, current experience with Syria C766 suggests minimum impact on the results. The results were achieved for concrete structure with relatively slender members. Therefore, further investigation of more stocky concrete members is recommended. A list of references is being presented. The authors sincerely appreciate Jacob's input into the design as a part of Design Joint Venture and RPS for Environmental Design. This is the end of presentation. Thank you for your attention. Should you have any questions, please send me an email.